Good evening, May 16, 2023, Tuesday. Warm, less warm than the record high temperatures yesterday and the day before, yet not cold. You know, I really am happy to find this a new E-day fix. And what's an E-day fix? Well, an E-day fix is generally described as something that, with regards to, it's usually considered pathological. An E-day fix is something that forms as an otherwise unfounded assumption in the mind, something that becomes an obsession of a sort. And so here it's framed a little bit more positively as something that gains its own kind of standing, in the sense that something like an axiomless geometry or an axiomless natural deduction is itself its own kind of E-day fix, because it only arises from its own kind of rational support. And at the beginning or the outlay or the denouement of something like that, it involves getting to a lot of the basic fundamental logical paradoxes to really have an approach to it that results as not unfounded. So from these foundations, there's this general idea of some kind of idée, a French word for idea, fix, French word for fixed, that arises that this way. It's kind of a thing. And so it's also just kind of something that is just a regular notion, or something that finds itself of central character or importance or something like that. And so in that sense, it's framed in essentially a positive light. And in that, with regards to the dialectic and the analysis, what results is when it arrives that such an idea is to be put down because it's fallacious or disproven or inconsistent or contradictory, as with others, basically, or beliefs, that the idea fix is a belief. That here it's kind of amused me very much in the study of the differential analysis to take a look back at it from having a mathematics degree, and so going through a curriculum up through ordinary differential equations and dynamical methods and this sort of thing, including like probability theory, which is largely framed in the calculus, and advanced calculus, or a calculus, within 7 or 8 different courses or more, and only just an undergraduate curriculum, say, and compared to something that gets involved when you get up to something like this PDE's basic theory, that this is quite an extensive kind of a novel that gets into lots of different aspects of what's in the partial differential equations in the modern setting, where we have differential equations and their solutions. This something like this ordinary differential equations from the University Mathematical text is much more along the lines of plane curves and their integral equations. It's so reversed, and it's really enlightening to consider the dialectic of the complementary duals that get so involved with that, because in that manner then it's 2 different viewpoints, and each of them has their strengths, and each of them has their ongoings. All these different books are full of things to do with the differential systems and differential equations, from hypersurfaces that the surface is generally considered a 2-dimensional surface in 3 dimensions, this sort of thing. Compared to volumes, the surface is only the boundary, and quadrature and the covariant derivative and such. A property of the intrinsic geometry, the covariant derivative. That that something becomes kind of possible of becoming a central idea when it's central, it finds itself in many, many situations. So mathematics itself is a central idea, due, for example, the ubiquitous success of mathematics in physics, and the ubiquitous success of mathematics in all manners of computation, and the ubiquitous success of physics in explaining things. And this then gets into, for example, the Christoffel symbols, and we covered them quite thoroughly in discussing those within the nonlinear electromechanical effects and applications. And once one gets beyond the preliminaries, the required, the basic, and the fundamental in the mathematics and arithmetic and algebra, and here there's been considered various approaches to deconstructive accounts of how those have elementary aspects and even more fundamental and elementary aspects into the theories of arithmetic and algebra and function theory and geometry, operator calculus, and number theory, category theory, theory of boundaries, theory of sets, theory of parts, all one theory. That it essentially, fundamentally, there's a mathematical theory where the objects of mathematics are one whole theory, a universe of the objects. For some, it's the same as the physical universe, with room left outside for the idea fix of the spirit or that which is unprovable, that it does or doesn't exist, thus that it has room to exist and otherwise is an idea fix in a positive sense. That we get into, that it gets into lots of different families and systems, and those things which become what are called fundamental theorems often enough, or establishing properties, invariance, uniqueness. 4D, the fundamental theorem of the local theory of surfaces, Gauss-Weingarten, Euclidean motions. That then it gets into when those objects are defined, these fundamental theories for these fundamental elements of these micro theories, mini theories, planks, platforms, way up above the foundations in terms of properties like orthogonality, points and curvature, principles, the ISO, parameters, and such in terms of the arithmetic and algebra. Here, for example, for the symbols, that then is arrived in terms of functions like gamma and the elementary functions and the sinusoidal functions and other families of orthogonal functions and sums and their sums and products, special functions, not usual non-standard functions like the Dirac delta, Heaviside step, which is about as simple as a waveform seems to be. From the left, it's 0. At the origin, it steps up 1, and then from the right to the right, it proceeds 1. Heaviside's step function. That just because it's vertical in a point makes it so that we in our field we just have a hard time dividing by 0 and analyzing any curve that has a vertical section. Then this whole notion of these plane curves and their integral equations goes a long way for that. Then in terms of, as we talk about, these singular points in that. Then another way to kind of reduce that has been this framework here of that, let's just start with positive numbers and the identity function, or x equals y, y equals x. And so that then we can develop families of functions about those is, all we're going to really care and deal with are positive magnitudes and functions that are defined, for example, as symmetrical about y equals x, or as about a family of functions that proceed down from 1 over x. And when I say down, I mean down the line that from the origin out through the identity function graph or chart, or geometrically through it. Or the Gauss-Bonnet theorem. So this is one of the most important theorems in all of differential geometry. It expresses what appears at first sight to be a surprising invariance of the integrated Gaussian curvature or its mean value. Yeah, Gauss has quite a few things that seem kind of contradictory to intuition sometimes. Visualize as follows. Consider a two-dimensional surface element with a boundary curve, so we call this like our configuration space, and make a change in the surface. So this is what we call a deformation. For example, like the ones we met in the consideration of minimal surfaces, we now require that this change preserves not only the boundary curve, but also a neighborhood strip of the boundary. In other words, only changes are allowed which vanish near the boundary curve. Then the integrated Gaussian curvature is also unchanged. Well, that's nice. And so it's expressed that this integrated Gaussian curvature is as of some kind of contour integral in terms of one of these plane curves around the boundary of the surface, and that it's an invariant quantity in terms of changes otherwise within the thing that make it so that if you can establish that those are equal, then it leaves it as one thing. And it reminds me of this when we were talking about the in the transmission of waves across surface is one thing, surface waves, and then in the surface skimming that have a certain depth that they reach to. And then when it got underneath that, then there was some questions about how to identify that in terms of the region. So there was readings from the path integral about that, and also readings from in the nonlinear electromechanical analysis about that, about how to figure out where the limits of differences would be, and to reduce it to those. And so then being able to close the surfaces, then being able to assign anything that goes across this invariant boundary as conserved, in the sense of like, well, we squeeze the balloon, and on the left and on the right combined, it's got all this volume, and no matter how you squeeze it, it's got the same on the other side. And so these kinds of statements then become quite intuitive. The change accounts for just as much additional positive as negative curvature. In particular, there is no non-trivial condition for the corresponding variational problem, as in 3.28. So then, when he talks about a variational problem, and that's a very interesting thing, the hypothesis of small perturbations, the virial, the variational, about the adiabatic and non-adiabatic, in terms of when we get into these situations in the systems that have the 1/2, the factor of 1/2. Well, why is that factor of 1/2 in there? Well, empirically, it's always been the case that you have to add it in, so we had to make a special case for random motion, whether random motion gets into or out of a fixed area or not, that it's basically linear motion or radial motion. That results in those two kinds of things that reflect two kinds of quantities and properties about whether curvature exists or straightness exists, as it were. And so this was discussed some, and this talks about the analysis and methods. And it gets into the Cantor space, all the zeros and ones, all the sequences of zeros and ones, and the square Cantor space, where Georg Cantor is famous for set theory and the uncountable. And so a Cantor space is considered a list, or as it were a table that looks like all the sequences of zeros and ones, and it's uncountably long. Well, it's infinitely wide, but it's also uncountably infinitely long. Whereas a square Cantor space is like, well, it's zeros all the way across the top, and half zeros and half ones in each column, and there's a bottom to it, and it's ones all the way across the bottom. And so the diagonal, if you read it off from the top, looks like 0, 0, 0, 0, 0, 0 also, because they're in order. And then it's the diagonal is at the end, so it's countable, and it's square, and it's not a Cartesian function. What so established it, this arranging in an order with both the order of the radix in the integral moduli, the moduli, and the order of the items, because they're determined by these iota values, like in Aristotle's continuum, or if you had the Zeno's paradox, but every time there was a split in half, then every time after that was also split in half. So everything is divided down to infinitesimals. And then that it exists as a continuous domain as a thing. But the point is about that in terms of the discussion of this random sequences and random elements from those is about how they have various distributions in these different models of these out in the large numbers, that they're weak and strong, and various laws of large numbers that are going to apply defined by how the effective infinity is defined. So again, and that's the idea of the infinity exists is its own kind of idea itself. For example, that it doesn't. Well, if you think an infinity exists, actually at least two models of infinity exist. If you think that an ordinary infinity exists, there's also just dealing with a fragment. But then there's also, if you think that an ordinary infinity exists that doesn't contain itself, there's also an extraordinary infinity that exists. There's no standard model. There's always either a fragment or the extension for there to be the model of an infinity in something like axiomatic set theories, descriptive set theories account of topology and geometry and number theory and . It's foundations. The idea is foundations. Like, we have to make one theory that everything fits in, and that's it. And then it's back to this book, talks about the Gauss-Bonnet theorem, or Bonnet, Gauss-Bonnet. And in order to prove this theorem locally as well as globally, we reduce it to the theorem on turning tangents in 2.28 and the theorem of Stokes. Now, what I'll be interested in here is on the theorem of turning tangents, 2.28. And I'm getting back to this chapter 3 after talking about the linear fractional equation. It made me very happy about the linear fractional equation, because this x equals y, then, and it's not a linear fractional equation, but it's right in the middle of all of them, because the discriminant of its coefficients, as it were, or AD minus BC, as it were, when it's built up in a matrix like ABCD, reading across a square 2 by 2 matrix, and taking the determinant of that as the discriminant, or what it is, that AD minus BC is left out. Here, that's just for the algebraic considerations. They got into some very interesting things, because there's otherwise, when we've already just limited the planar curves to this one area, and then there's also built up these symmetries in this outside of the box about them, that ends up being singular and original and all that kind of stuff. So it's special and it's central, and it's part of the EDA. So this 2.28. So there's Mobius strip, surface integral, a sphere with spherical coordinates, the local theory of surfaces. 2.32, total absolute curvature. There's various definitions of curvature. Here we've been talking about the sawtooth wave, but that the tooth is round, not pointy, but its curvature is infinitesimal. And that's what happens when you take 1 over x and tip it over onto its legs, so that it stands up with the point on top. And then shrink that to the unit square and make it look like a sinusoidal function among other families of orthogonal functions. Oh. Theorems on turning tangents. So this has a diagram of sorts, and the diagram's kind of interesting, because the diagram looks sort of like this unit square filled in above the identity. Filled in above the identity. It's after Hopf, H-O-P-F. Okay, that's the starting point here. Theorem on turning tangents. Let C of A comma B, this region, go to R squared, be a simply closed regular C2 curve. So it's twice differentiable at least. Then we have 1 over 2 pi equals integral from A to B, kappa T times determinant of C dot 2t dt equals UC equals plus minus 1. Surely there is a tangent such that the curve lies completely on one side of the tangent. By choosing now surely is often a thing, and I'd have to read back and just find what he describes as what is a curve, and make sure that it includes, for example, circles and other plane curves. Lies completely on one side of this tangent. By choosing as appropriate coordinate system, further assume that CT equals xt yt with ya equals yb equals 0, yt greater than 0 for all t. So he's established some initial conditions, and then he just defines this area of st and r squared such that the area is as was shaded, and as well as E, area A goes to R squared minus the empty set, or 0, leaving out the origin, kind of like yesterday or last time we were talking about the origin and whether or not it's a member, or whether it's a singular point, and whether it's a nodal point, and whether it ends up being that it has all these trivial and vacuous properties, and it's because it's a singularity, and when and whether it's really as of a vertical or horizontal line, or that otherwise it really expresses a spiral from the origin, and when and whether, according to the linear fractional equation, then off this very simple build out, it gets imaginary in the sense that there's complementary duals up and about it. The dot dot dot, the wonderment of the E-day E of st equals these three cases. In case s equal t and st is not equal to ab, then it's ct minus cs over the determinant is ct minus cs. And I'm reading that might be the normal, it might just be like the normal of those. And I need to make sure that now that I've gotten into differential geometry, that the same definitions hold, or that something's looser or tighter that would need to be kept relevant. In case c dot t over c, that norm of c dot t, in case s equals t, which here it would, yeah, because that's the special case of that. And reducing that also the unit box, so we'll leave it as this one thing there. And c dot a over negative c dot a in case st equals ab. Since the curve is simply closed, one has ct not equal to cs for all t not equal to s except st equals ab. So those are the endpoints in a sense, and oh, the curve is closed. So that's nice. So this section has a global theory of curves, so I'm going to go back and start at the beginning of this to relate it to our plane curves that we're getting out of the old school or the old-fashioned development of the integral calculus. That's the differential calculus as an integral calculus. So what we have here is the continuity of E follows from the continuous differentiability. This is easily verified by passing the limit from the secant to the tangent. So passing the limit from the secant, like sine and cosines, secant and cosecant. Passing the limit from the secant to the tangent would be as of some trigonometric exercise, and when it goes from cosine over 1 to cosine over sine, it might get worked up in terms of when it's not so that sine x over x is indeterminate. Clearly, ETT is a unit tangent of the curve CT. Yes, that would be so for this identity function because it's the same. According to 0.27, there exists a polar angle function of psi. A goes to R, or let's say phi, A goes to R with EST equals cosine phi TS, sine phi TS, and phi A comma A equals 0. A. The function phi t equals phi t. T is then the polar angle function along the curve CT. Hence, it is differentiable in t, and by that we have 1 over 2 pi integral from a to b of k kappa t, norm c dot t dt equals 1 over 2 pi integral from a to b phi t dt equals 1 over 2 pi quantity phi b comma b minus phi a comma a. Well, and that's 1 over 2 pi then, phi b comma b phi a comma a, the polar angle function, so it's an angle in that, and it would look like 1/2, so it would be pi b b, and phi b a equals 1. So in this case, it doesn't need much more than 1, it's sine or cosine. In the case where the example of this theorem on only this curve has certain particulars that make other necessarily things to fill out the general drop out because they're specific or vacuous. And so when treating then furthermore the requirements on the function for these kinds of applications after the derivation, it does or doesn't, here it doesn't have these strictures that would be necessary to keep it well defined. On the other hand, psi a comma b minus psi a comma a equals pi, in case x dot a greater than 0, otherwise equals negative pi, and also psi b comma b minus psi a comma b equals pi in case x dot a greater than 0. Well, here it just equals pi, otherwise equals da da da. This is verified upon consideration of the polar angle for the family of all secants, ct minus c on the one hand and cb minus cs on the other. In sum, we have that psi of b comma b minus psi of a comma a is either plus 2 pi or minus 2 pi. Actually, here it's just pi. But it's interesting to look at that for a moment and figure out how it's kind of like so. The total absolute curvature. So going back to the global theory of curves, then there's a start that curves are defined as space curves, plane curves, and space curves. Oh, it mentions the catenary, the tractrix, names of curves, curves in Rn. So that would be it. In the practical world, curves arise in many different ways. From this point of view, the association of the parameter t, the position c to t is important, so they're defined by functions in a parameterized curve. From the real-world notion of a thin object, one which has no width whatsoever, one-dimensional, infinitely thin object, parameterization and the curve are supposed to have reasonable properties which allow an acceptable mathematical treatment. A short introduction to the theory of curves can be found in a reference, but we will not assume any familiar with this on the part of the reader. One can define a curve most easily as continuous mapping from an interval to Rn. So with the domain being an interval in R, and so we'd call that a continuous domain, say, and having a continuous function between the two to say this other space where we have y equals x, we'll also call that R. Unfortunately, the assumption of continuity is so weak that curves defined in this manner can look very complicated and have unexpected pathological properties. Not necessarily. There are continuous curves which cover a whole square in the plane. Well, this is called a space-filling curve, and so here there's already included a non-standard basic fundamental spiral space-filling curve. And then that a mapping that is, and it's kind of extra continuous because not only are its points connected and differences between its points are connected, but it builds out that points are basically in moduli lines. So it builds a lattice compared to basically the only way you can imagine a spiral space filling curve is starting from the inside and going out. A spiral space filling and non-crossing curve is being in the inside and going out, or being in the outside and going in. Because via deduction, if it didn't necessarily fill outward a tiny, tiny, tiny infinitesimal square on its way out, it can never get back inside the track. Though I suppose there is some notion of a left and right bit, as one can imagine a space-filling curve or square that would go left to right in a scan line is what it's called, in something like picture elements or a raster after the rake of the image, the coordinates of a square image, left to right and then right to left and left to right and right to left. Again, if we reduce your space-filling curves to non-crossing space-filling curves, quite simplified, then the idea of this space-filling curve, the spiral that could actually go to the reach to the edge and then come back and turn around and fill in what was left inside, that's basically the first part of it draws a Archimedean spiral or just any sort of open spiral, and then goes back in and out into like the shell on the desk, like the conch shell or the cornucopia or something like that. that can be built up with any number of properties. So here the author has just made clear that there are continuous curves which cover a whole square in the plane. And